In part two of solving equations, we're going to look at some more complex equations, linear equations, and also some techniques you can use to try to minimize your chances of making a mistake. So here's a fairly typical linear equation. We have an expression on the left, 5x minus 4, and an expression on the right, 7x plus 6. Unlike all the examples I gave you in part one, where we only had one instance of a variable, here we have two. We've got the 5x on the left, we've got the 7x on the right. So the first step normally in solving this particular type of equation is to collect the like terms. And that just means get the expressions involving the variable onto the same side of the equation and collect them, meaning add them together or subtract if necessary. So we have a choice here, and when I see students solving this sort of equation, I generally see them wanting always to bring the variables over to the left-hand side. So what that would look like is we subtract 7x from both sides. So remember that you're allowed to do the same thing to both sides of an equation. So if we subtract 7x from the left and we subtract 7x from the right, we're doing the same thing, so that's fine. What happens on the right, the 7x minus 7x, that whole thing just disappears. So on the left, we have 5x minus 7x. That's the collection. That's what we're going to simplify and write that as minus 2x. And now we can just complete this the same way we did all the examples in section 1 or part 1. Here we would add 4 to both sides, so minus 2x minus 4 plus 4 equals 6 plus 4. And that leaves us with just minus 2x on the left and 10 on the right. And so to get x on its own, we need to divide by the coefficient minus 2. So we get 10 over minus 2. And finally, we end up with x equal to negative 5. We can check this, right? We can plug in the negative 5 to the original expression on the left. 5 times negative 5 would be negative 25. Minus 4 is negative 29. And when you plug the negative 5 into the expression on the right, you get 7 times negative 5, which is negative 35, plus 6 is negative 29. So this is the correct solution. And there's nothing wrong with doing it this way. But let me suggest an alternative. So an alternative would be to collect the terms on the right-hand side. And that would look a little different. So instead of subtracting 7x from both sides, our first step would be to subtract 5x from both sides. And you can see that the 5x would now disappear on the left, and all we'd be left with is negative 4. So then we'd have 2x on the right. And at this point, it's pretty straightforward. We can subtract 6 from both sides. So 2x plus 6 minus 6, and negative 4 minus 6. The left-hand side gives us minus 10. The right-hand side, just 2x. Then we can divide both sides by 2, and we get negative 10 over 2. And so we end up with the same thing, x equal to negative 5. And there's certainly nothing wrong with having the x on the right-hand side. You can read it, an equation can be read from left to right or right to left, so we have x equal to negative 5. So we get the same thing. So you may be wondering, well, what's the point? Well, what I notice when I solve equations, and I certainly notice this with a lot of students, there's some kind of mental quirk that arises when you divide by a negative. So if you look at the left-hand side, a couple lines from the end, we had 10 on the right-hand side. Then we divided both sides by negative 2. The 10 became negative 5. So there's a sign change in there, and that's what gets dropped. That's what gets missed, and a lot of students end up making a mistake in writing the final answer as x equal to 5. On the right-hand side, if you notice, we already had the negative 10, and that arose just from subtracting 6 from negative 4. Now, for whatever reason, our brains are better able to handle that sort of thing, and we are much less likely to make a mistake when we're adding and subtracting. So we already have the negative 10 on the left-hand side, and then we're dividing by positive 2. There's no sign change there. So it was negative to start. It is negative once we divide by 2. And this just seems to be a much safer way to do it. So I always go out of my way, even when it requires an extra step. You'll see some of the equations require kind of an extra step to do this. But if you really want to minimize your chances of making a mistake, you might want to consider doing something like this. All right, so now let's look at some slightly more complex equations involving fractions. So what if we have something like 3x minus 1 over 2 equal to 4x plus 3 over 3? So my suggestion when you're solving equations is if you have fractions anywhere, you should try to get rid of them. The first step should be multiply both sides of the equation by some number that gets rid of all the denominators. And that number that you're going to multiply both sides of the equation by is the lowest common denominator, or the least common multiple of the denominators. In this case, 2 and 3, the least common multiple there would be 6. So one way is just to multiply both sides by 6, but you can actually get a better idea of what's really going on if you just, instead of writing it as 6, you multiply both sides by 2 and both sides by 3. That's the same as multiplying both sides by 6. But now it's pretty obvious that what's going on is on the left-hand side, the 2's are canceling. So these 2's disappear, leaving me with just 3 times that numerator, 3x minus 1. And on the right, the 3's are canceling, leaving me with the 2 times that numerator, 4x plus 3. Now, a lot of students refer to what I just did as cross-multiplying. And that's fine. You can call it cross-multiplying if you like. You have to be a little bit careful, though, because students end up applying this technique of cross-multiplying in inappropriate situations, and we'll see one in the next example. But in this case, you have to keep in mind that it's an equation, and the way you get the cross-multiplication is by really multiplying both sides by the same thing. So let's continue this. We can now expand, and notice we have no fractions, right? So this is the good thing about this method. So now we have 9x minus 3 on the left, and on the right we have 8x plus 6. And once again, we've got x's on both sides. Let's collect them. We can subtract 8x from both sides. So my choice is always to try to collect the x's on the side that give you a positive coefficient. And since we have 9 on the left and only 8x on the right, it makes sense to collect them on the left. So we're going to subtract 8x from both sides. And that will get rid of the 8x from the right and leave us with just a single x on the left. And now we can just simply add 3 to both sides. And if we add 3 to both sides, we get 6 plus 3. So we end up with x equal to 9. We can check this pretty easily. Let's plug it in back to the original expressions. 3 times 9 is 27, minus 1 is 26, divided by 2 is 13. So the left-hand side and the original expression was 13. On the right-hand side, we have 4 times 3 is 36, plus 3 is 39, divided by 3 is 13. So this is the correct equation. Now, at this point, I want to just suggest that after you've done these sorts of equations a number of times, there are some steps that you can not really leave out, but not necessarily write down. And all of these steps you should think of as a form of communication. You're communicating to somebody how to solve this equation, and you're justifying that the answer you have is the correct answer. If you don't write down any steps, nobody else is going to be able to understand what you've done, and they may not have all that much confidence in your answer, short of actually just plugging it in. Now, if there's a mistake, you're not really going to understand or get any insight into where you went wrong. But there's sort of an idea of who your audience is. And so if your audience is somebody who's fairly sophisticated in solving equations, has done lots of them, and quite frankly, most of the time your audience is yourself a few hours or days into the future, then you can kind of leave out some steps because they're the obvious steps. So for instance, this line right here, we can leave that out because to go from 9x minus 3 equals 8x plus 6 to the next line, x minus 3 equals 6, it's obvious what we've done. We've subtracted 8x from both sides. And after you've done this many times, you'll see that. Similarly, we can leave out this line right here because, again, if you're at x minus 3 equals 6, there's not a huge jump to x equals 9. It's obvious that you just added 3 to both sides. And so that just cleans it up a little bit and requires fewer lines, makes it more readable. So think about that when you are solving equations. You want to put in enough information so that it's obvious what you're doing, but not so much that it ends up kind of cluttering the page. All right, so let's take a look at another example. This one, again, similar, but a little bit more involved. So what if we have 2 times 5 minus x all over 3 equal to 3 times 2x plus 1 all over 5. So once again, my suggestion, first step, get rid of the fractions, multiply by the lowest common denominator, which would be 15, or the least common multiple of 3 and 5. Again, if you just write it as 3 and 5, you'll see that what happens is you end up canceling out on the left the 3's and on the right the 5's. So what do we end up with? We end up with 5 times 2, which is 10, times this expression in brackets, 5 minus x. And on the left, we have the 3 times the 3, which is 9, times the 2x plus 1. You could, of course, have expanded the numerators, the 2 times the 5 minus x. I chose not to. I chose to try to get rid of the fractions first. There's always going to be a lot of choices when you're solving equations, and you'll have to do this a number of times before you develop some idea of what steps you like to do first. So let's go ahead now and expand this. 10 times 5 is 50. And the 10 times the minus x becomes minus 10x. And then on the right, we have 18x plus 9. So again, which side are we going to collect the x's on? So if I collect the x's on the left, that means I'm going to be subtracting 18x from both sides, and I'm going to have negative 28x. I don't like having that negative coefficient. So I'm going to collect the x's on the right by adding 10x to both sides. And if I add 10x to the left, it disappears, leaving me with 50. If I add 10x to the right, I get 28x. Okay, so I've left out the explicit writing of minus 10x on both sides. And then again, if I subtract 9 from both sides, I'm going to end up with 41 on the left and 28x on the right. And now I can divide both sides by 28, and I end up with 41 over 28. So I've left out those sort of explicit steps where I do the same thing to both sides, but it's fairly obvious going from line to line what I've done. This obviously is a bit more challenging to check. 41 over 28 is a fraction, can't be reduced, and it's about 1.5. You can certainly plug in 1.5 to get an idea of whether you're in the right ballpark. 5 minus 1.5 is 3.5 times 2 is 7. 7 over 3 is a bit more than 2. On the right-hand side, we have 1.5 times 2 is 3, plus 1 is 4, times 3 is 12 over 5, which is a bit more than 2. We're kind of in the right ballpark. If we got something way off, I'd want to take a closer look at it. Let's take a look at one more example, because once again, this example I gave you, you could have just said, all right, let's cross multiply. But if you notice this example and the previous example, the original expression on the left was a fraction, a single fraction, and the expression on the right was a single fraction. If you don't have a single fraction equal to a single fraction, then you definitely cannot do cross multiplying. And let's take a look at an example where you can't. So if we have x plus 1 over 2 minus 5 on the left, and on the right we have 2x minus 1 over 3 plus a quarter. All right, so we've got kind of fractions all over the place, some involving variables and some not. We've got 3 different denominators there, a 2, a 3, and a 4. So here's where you really just start wanting to think about what is the lowest common multiple of those denominators. So the LCM of 2, 3, and 4 is 12. All right, so 12 has a factor of 2, has a factor of 3, has a factor of 4, and there's no smaller number that does that. When we multiply the left by 12 and the right by 12, we're going to get rid of all the fractions. You have to be very clear on this. The next line should have no fractions whatsoever. So sometimes I see students follow this technique, but then the next line has fractions all over the place and just bigger numerators. That's definitely not the goal here. The goal is to get rid of the fractions. And if you've picked 12 correctly, it should cancel with all the denominators. So the first product we're going to do is 12 times the x plus 1 over 2, and then the second is going to be the 12 times the minus 5. When you do that first product, the 12 divided by 2 becomes 6. And so you just end up with a 6 times that numerator x plus 1. 12 times minus 5 is just minus 60. On the right, we have 12 times 2x minus 1 over 3 and 12 times a quarter. So 12 times 2x minus 1 over 3, do the division first. 12 divided by 3 is 4. So that leaves you with a 4 times the numerator. And 12 times a quarter is just 3. All right, one line, no fractions. That's exactly what I wanted. Now I can expand those two terms that have brackets. So I end up with 6x plus 6 minus 60 on the left, 8x minus 4 plus 3 on the right. The plus 6 minus 60, let's simplify things that are easy to simplify. So we have 6x minus 54. On the right, we have 8x minus 1. All right, so which side are we going to collect the x's on? Well, I've got 8x on the right, 6x on the left. My choice is let's collect the x's on the right. I'll do that by subtracting 2x from both sides. And I'll add 1 to both sides at the same time. And so, I sort of did 2 steps in one there, but going from that second to last line to that last line, I think most people who've solved a few equations are going to know what steps I took. And then the final step is to divide both sides by 2, so you get negative 53 over 2. Again, not the easiest number to plug in and check, but not all that hard either. Negative 53 over 2 is about negative 26, negative 27. It's actually negative 26.5. If you plug it into the expression on the left, you get negative 26.5 plus 1 is negative 25.5 divided by 2. That's about negative 13 minus 5, roughly about negative 18 on the left. On the right, when you plug it in, you get negative 53. All right, the 2's cancel. Minus 1 is negative 54 over 3, which is 18, plus a quarter. Again, it's about 18, or rather negative 18. So they are roughly equal with our just sort of rough approximation, and that's good enough. If we got something really different, we would definitely want to take a closer look at it. So, these techniques take a lot of practice, and what also takes a lot of practice is getting comfortable with which steps to do first, because depending on the numbers, depending on the equation, you may not always want to do the steps in exactly the same order that I've just done them, but that's going to be a matter of fluency from you trying lots and lots of equations.